Today we will look at some problems about homework 13. For the first problem, we need to find the flow rate. And we assume this is 0.1 and this is 0.2. And we assume 0.1 is datum. And we know the distance between 0.1 and 2 is 30 meters, so we can, and we also know the slope of pipe is 1/10, so we can determine that h is 3 meters. And then we apply the energy equation between 0.1 and 2. So we have P1 over gamma plus V1 squared over 2G plus Z1 should be equal to the P2 over gamma plus the V2 squared over 2G plus Z2 plus HF. And we know the P1 is 150 kilopascal, and P2 is 120 kilopascal, and Z1 is datum, so it is 0, and Z2 should be equal to the h. It is 3 meters. And since the diameter of pipe does not change, so the V1 should be equal to the V2, and the gamma should be equal to the rho times G, and we know the rho is 800 kilogram per cubic meters. So we can determine that the HF, the hair loss, is 0.823 meters. And then we need to find the resistance coefficient, the F. To find the F, we need to compute the parameter. This parameter is D to the power of 3/2 divided by the nu times the root of 2G times HF over the L. Yes. And from the problem, we know the D is 0.08 meters, and the nu is 10 to the power of -6 square meters per second, and the length is 30 meters, and we know the HF is 0.823 meters. So we can determine that D 3/2 times square root of 2G times HF times L should be equal to 1.66 times 10 to the power of 4. And then we need to calculate, we also need to calculate the relative roughness, the Ks over D. And from the table 10.4, we can find that the Ks is 1.5 times 10 to the power of -4 meters. And we also know that D is 0.08 meters, so we can determine that the relative roughness Ks over D should be equal to 1.9 times 10 to the power of -3. And then we look out F on the multi-diagram. So this is multi-diagram. And we calculated the case over D this is 0.0019. So the curve should like this. Sorry. The curve should like this. The curve maybe like this one, and we also know this parameter is 1 point, maybe this is 1.66 times 10 to the power of 4. So and sorry. And we can find maybe the intersection. I found the F. Maybe so we can find the F. Maybe it's 0.025. So F from the multi-diagram, we found out F is 0.025. And then we know HF should be equal to the L over D. The HF should be equal to the F times L over D times V squared over 2G. And we know the HF is 0.823 meters, and the F is 0.025, and it's L is 30 meters. The D is 0.08 meters. So we can determine that the V is 1.312 meters per second. And we know the Q should be equal to the A times V. So it is pi times D squared over 4 times V. So it should be equal to the pi times 0.08 meters square over 4 times 1.312 meters per second. So we can find that the Q should be equal to 6.59 times 10 to the power of -3 cubic meters per second. So we finished this problem. For the second problem, we need to find the diameter of pipe and the pump power. So from the Darcy equation, we have that the HF should be equal to the F times L over D times V squared over 2G, and also equals the F times 8 times L times Q squared over G times pi squared times D to the power of 5. And solve for diameter, so we have the D should be equal to F times 8 times L times Q squared divided by the G times pi squared times HF to the power of 1/5. And we consider this equation as equation 1. And for the first iteration, we assume F is 0.015, and we know so L is 1,000 meters, and the Q is 0.1 cubic meters per second, and the HF is 50 meters. So we can determine that based on the equation 1, we can determine that the D is 0.19 meters. And now we can determine the Reynolds number. We know R E to be equal to the 4 times Q divided by the pi times D times the nu, times the nu, when the Q is 0.1 cubic meters per second, and D is 0.19 meters, and the nu is 10 to the power of -5 square meters per second. So we can determine the Reynolds number is 6.7 times 10 to the power of 4. And then we can use this equation F to be equal to 0.25 divided by the log 2 the base 10 of the Ks divided by 3.7 times D plus 5.74 divided by array those number to the power of 0.9 square. And then we can use this equation to find the new F. And we consider this equation as equation 2. Actually, this equation is equation 10.39 in your textbook, and Professor Diblas also provided these equations on the lecture number 20. And now we know the D is 0.19 meters, and the Ks from the table 10.4 in your textbook, we can find that the Ks is 4.6 times 10 to the power of -5 meters, and we know the Reynolds number is 6.7 times 10 to the power of 4. So based on the equation 2, we can find that the new F is 0.021. And now for the second iteration, we assume the F is 0.021, and based on the equation 1, we can determine that the D, the new diameter nu d is 0.203 meters. And now we can also calculate the Reynolds number. Should be 4 times q divided by pi times d times nu, and we know that d is 0.203 meters, so we can determine the Reynolds number is 6.3 times 10 to the power 4, and we know the Reynolds number, and based on the equation 2, we can find that the nu f also is 0.021. So the friction factor does not change. So we can find that the diameter of this steel pipe, the d, should be equal to the 20.3 centimeter. And we will use the next larger size of pipe. So the pipe should be 22 centimeter. So can determine that d should be equal to 22 centimeter. And then to calculate the pump power, we will apply the power equation. So for the power equations, the P should be equal to the Q times gamma times the HF. And we know that Q is 0.1 cubic meters per second. And the gamma of oil should be equal to the Sg oil times the specific weight of water at the 4 degrees Celsius. From the problem, we know the Sg is 0.93, and the specific weight of water at 4 degrees Celsius is 9810 newtons per cubic meter. And we know the HF is 15 meters, so we can determine that the P, the power, should be equal to the 45.6 kilowatt for each kilometer of pipe length. So we finish this problem. For the third problem, we need to find the pump power and sketch the HGL and the EGL for the system. And we are shown the reservoir surface. This reservoir surface is 1, and this reservoir surface is 2. And we apply the energy equation between the 1 and the 2. We have P1 over gamma plus V1 square over 2G plus Z1 plus HP should be equal to the P2 over gamma plus V2 square over 2G plus the Z2 plus the total head loss. We know the V1 should be equal to V2 equals 0, the P1 equals P2 equals 0, and Z1 is 100 meters, Z2 is 112 meters, and the total head loss in this problem should include the pipe hair loss and the minor hair loss. So the minor hair loss includes the hair loss for the pipe entries and the hair loss for the expansion. So the HL total hair loss should be equal to the pipe hair loss, the F times L over D times V squared over 2G, and plus the minor hair loss for the entries. So the KE, the coefficient for the pipe entries hair loss, times V squared over 2G plus the K uppercase E times V squared over 2G. So now we can find that the HP should be equal to the 12 meters plus the V squared over 2G times F times L over D plus the K lowercase e plus the K uppercase E. And to find the HP, we need to calculate the velocity in the pipe and the friction factor and the coefficient, these two coefficient factor. So we know that the V should be equal to the Q divided by the A should be equal to the Q divided by the pi times D squared over 4. And we know the Q is 0.3 cubic meters per second, and D is 0.3 meters. We can determine that the velocity V is 4.24 meters per second. And now we can determine the Reynolds number. So RE should be equal to the V times D divided by the nu. And we know the V is 4.24 meters per second, and the D is 0.3 meters. The nu is 10 to the power of negative 5 square meters per second. We can determine the Reynolds number is 1.27 times 10 to the power 5. And from the table 10.4, we can find the KS should be equal to the 4.6 times 10 to the power of negative 5 meters. And then we will use these equations. F equals 0.25 divided by the log 2 the base 10 of KS divided by 3.7 times D plus 5.74 divided by RE to the power of 0.9 square. We can use these equations to calculate the F. So we know that D is 0.3 meters and the KS is 4.6 times 10 to the power of negative 5 meters, and Reynolds number is 1.27 times 10 to the power 5. So we can determine the F is 0.018. And then from table 10.5, we can find the head loss coefficient for the pipe entries. And I think from the table 10.5, I think R divided by the D should be greater than 0.2 for this problem. So I determine that the coefficient of the minor coefficient for the pipe entries for this problem is 0.03, and for the expansion head loss coefficient, we can find that the K uppercase E is 1. So now we can determine that the HP should be equal to the 12 meters plus 4.24 meters per second square over 2G plus, times the 0.018 times the L, the mass is 150 meters divided by 0.3 meters plus 0.03 plus 1. So we can find that the HP should be equal to the 21.19 meters. And then we apply the power equation. The power should be equal to the Q times gamma times the HP. And we know the Q is 0.3 cubic meters per second, and the gamma should be equal to a rho times G, equal to the rho is, let me check, 940 kilogram per cubic meter. So 940 kilogram per cubic meter times 9.81 meters per second square. And we know the HP is 21.19 meters. So we can determine that the P, pound power, should be equal to 58.6 kilowatt. And now we need to sketch the EGL and HGL. And EGL should like this one. EGL should like this one. There is upper raptor rays. Then we'll go down. So this is EGL. And I will use other color green to plot HGL. The dashed green line is HGL. So we finished this problem. For the fifth problem, we need to find the minimum diameter of the pipe. And the method is similar to the second problem. So from the Darcy equation, we have HF should be equal to F times L over D times V squared over 2G. Also equals to the F times 8 times L times Q squared divided by the G times pi squared times D to the power of 5. And then, so for the diameter, we have the D should be equal to F times 8 times L times the Q squared divided by the G times pi squared times HF to the power of 1 over 5. So we consider this equation as equation 1. And for the first iteration, we'll show F is 0.015, and we know the length is 87 feet. Q is 2 cubic feet per second, and we know the head loss, maximum head loss is 3 feet. And according to the equation 1, we can get that the D is 0.53 feet. And now we need to calculate the Reynolds number. So the Reynolds number equals 4 times Q divided by pi times D times nu. And we know the Q is 2 cubic feet per second, and the D is 0.53 feet. And from the table A5, we know that when the water temperature equals 40 degrees Fahrenheit, we can determine that the nu is 1.66 times 10 to the power of -5 square feet per second. So now we can determine that the Reynolds number is 2.89 times 10 to the power of 5. And then we can use this equation to calculate the nu F. D plus 5.74 divided by the Reynolds number to the power of 0.9 square. We consider this equation as equation 2. And from the table, from the table 10.4, we can determine that the Ks equals 0, and we know Reynolds number is 2.89 times 10 to the power of 5. So we can determine that UF is 0.0145. And for the second iteration, the F is 0.0145, and based on the equation 1, we can determine that the D is 0.5332, and we can calculate the Reynolds number is 2.89 times 10 to the power of 5, and based on the equation 2, we can get that the new F also is 0.0145. So we can see the friction factor does not change. So the D should be equal to 0.53 feet equals 6.36 inch. So we need to use the next larger size of pipe. So we'll select a pipe with D. The diameter should be equal to the 8 inches. So we finished this problem. For this problem, we need to find the difference in what is surface elevation between the two reservoirs. The first, we calculate the relative roughness for each pipe. So the Ks divided by the D1 should be equal to 0.1 millimeter divided by 120 millimeter. So its value is 8.3 times 10 to the power of -4. For the pipe 2, the Ks divided by the D2 should be equal to 0.1 millimeter divided by 240 millimeter. So its value is 4.2 times 10 to the power of -4. And then we calculate the velocity in each pipe. So the V1 should be equal to the Q divided by the A1 equals Q divided by the pi times D square, D1 square divided by the 4. So the value equals 0.1 cubic meters per second divided by pi over 4 times 0.12 meters square. So the velocity V1, the velocity is 8.842 meters per second. So the V2 equals Q divided by the A2 equals Q divided by pi times D2 square over 4 equals 0.1 cubic meters per second divided by the pi over 4 times 0.24 meters square. So the velocity in the pipe 2 is 2.21 meters per second. And then we can determine the Reynolds number in each pipe. So the Reynolds number RE1 should be equal to V1 times D1 divided by the nu. And according to this problem, we know that the temperature, water temperature is 20 degrees Celsius. So when water temperature is 20 degrees Celsius, we can determine that the nu, use the other color, the nu should be equal to the 10 to the power of -6 square meter per second. And we know the V1 is 8.842 meters per second, and D1 is 0.12 meters. So we can determine that the Reynolds number in pipe 1 is 1.06 times 10 to the power of 6. And Reynolds number in pipe 2 should be equal to the V2 times D2 divided by the nu. And we know the V2 is 2.21 meters per second. Sorry, meters per second. And the D2 is 0.24 meters. So we can determine that R Reynolds number in pipe 2 is 5.3 times 10 to the power of 5. And then we could determine the friction factor F for each pipe using this equation. So use this equation. Times D plus 5.74 divided by the RE to power of 0.9 square. So the F1 should be equal to 0.25 divided by log 2 the base 10 of 1 over 3.7 times 8.3 times 10 to the power of -4 plus 5.74 divided by 1.06 times 10 to the power of 6 power of 0.9 square. So we can determine that F1 is 0.019. Then we can determine that F2 to be equal to 0.25 divided by 10 over 3.7 times 4.2 times 10 to the power of -4 plus 5.74 divided by 5.3 times 10 to the power of 5 to the power of 0.9 square. So determine that F2 is 0.017. And then we apply the energy equation between the two reservoirs. And we're shown this is point A and this is point B. So we apply the energy equation. We have the PA divided by the gamma plus the VA square by 2G plus CA should be equal to the PB divided by the gamma plus the VB square divided by 2G plus ZB plus head loss. And we know the PA equals PB equals 0, the VA equals VB equals 0. And for the total head loss, the total head loss includes the pipe head loss and the minor head loss. So for the pipe head loss, the HL1 should be equal to the F1 times L1 divided by D1 times V1 squared divided by 2G. And head loss in pipe 2, F2 times L2 divided by D2 times V2 squared divided by 2G. And for the minor loss, the head loss at the entries should be equal to head loss at the entries. head loss at entries should be equal to the k lowercase e times v1 square divided by the 2g. And from the table 10.5, we can find that the k lowercase e should be equal to the 0.5. And the other minor loss is at the outlet of the pipe. So the HE should be equal to the k uppercase E times V2 square over 2G. That's this one. So from the table 10.5, we can determine that the KE should be equal to the 1. And for the sudden expansion in a pipe, when we know the velocity, we can use this equation to calculate the head loss. So HE to this means that the head loss for the sudden expansions should be equal to the V1 minus V2 square divided by 2G. Actually, this is equation 7.37 in your textbook. And now we have that ZA minus ZB should be equal to F1 plus L1 divided by D1 times V1 square divided by 2G plus F2 times L2 divided by the D2 times V2 square divided by 2G plus the coefficient for the pipe entries, k times V1 square divided by 2G plus the coefficient for the expansion at our pipe of outlets, so k uppercase E times V2 square divided by 2G, and plus the sudden expansion head loss in the pipe, so equals V1 minus V2 square divided by the 2G. And we know that F1 is 0.019, we have calculated before, and F2 equals 0.017, and V1 is 8.842 meters per second, V2 is 2.21 meters per second, and the key lowercase e equals 0.5, and the key uppercase E equals 1, so we can determine that ZA minus ZB is 44.45 meters. So we finished this problem. For the last problem, we need to find the water surface elevations in reservoir A, and we also need to draw the HGL and the EGL. And the method is very similar to the previous one. But first we should, this is pipe 1, and this is pipe 2. And we need to calculate the relative roughness for each pipe first. So from the table 10.4, we can find that the KS for this problem is 0.26 millimeter. And then the KS over divided by D1 will be equal to 0.26 millimeter divided by the 200 millimeters. So the relative roughness for pipe 1 is 1.3 times 10 to the power of -3. So the relative roughness for the pipe 2 equals 0.26 millimeter divided by 150 millimeter, and the value is 1.7 times 10 to the power of -3, and then we need to calculate the velocity in each pipe. So V1 should be equal to the Q divided by the A1 be equal to the Q divided by the pi times D1 square over 4, so equals 0.3 cubic meters per second divided by the pi, divided by the pi times 0.2 meters square divided by the 4, so the V1 is 0.955 meters per second. And the V2 equals Q divided by the A2 equals Q divided by the pi times D2 square divided by 4, so equals 0.3 cubic meters per second divided by the pi times 0.15 meters square over 4, so we can determine that the V2 is 1.698 meters per second. And then we can determine the Reynolds number for each pipe. So V1 D1 divided by nu, and we know the water temperature for this problem is 10 degrees Celsius, so we can determine the nu is 1.3 times 10 to the power of -6 square meters per second. And we know V1 is 0.955 meters per second. D1 is 0.2 meters. So we can determine that the Reynolds number in pipe 1 is 1.5 times 10 to the power of 5. And R2 equals V2 times D2 divided by the nu, so equals 1.698 meters per second times the 0.15 meters divided by the 1.3 times 10 to the power of -6 square meters per second. So we can determine that the Reynolds number in pipe 2 is 1.9 times 10 to the power of 5. And then we can determine the friction factor for each pipe. So the F1 should be equal to 0.25 divided by log to the base 10 of 1 over 3.7 times 1.3 times 10 to the power of -3 plus 5.74 divided by 1.5 times 10 to the power of 5 to the power of 0.9 and square. So we can find that F1 is 0.023 and F2 is 0.25 divided by 3 times 1.7 times 10 to the power of -3 plus 5.74 divided by the 1.9 times 10 to the power of 5 to the power of 0.9 square. So determine that F2 is a 0.024. And then we apply the energy equation between the reservoir A and B. So we have that the P PA gamma plus VA square divided by the 2G plus VA should be equal to the PB divided by the gamma plus VB square divided by 2G plus CB plus the head loss. And we know the PA equals PB equals 0, VA equals VB equals 0, and the total hair loss include the pipe hair loss and the minor hair loss. So for the pipe hair loss, so the hair loss in pipe 1 is equal to F1 times L1 divided by D1 times V1 square divided by 2G. Hair loss in the pipe 2 should be equal to the F2 times L2 divided by D2 times V2 square divided by 2G. And then we need the minor head loss. So the head loss at the entries should be equal to head loss at the entries should be equal to the K lowercase e times V1 square divided by the 2G, and from the table 10.5 we can determine that the Ka lowercase e is 0.5, and the minor hair loss for the expansion at the outlet should be equal to the K uppercase E times V2 square divided by the 2G. So this is this outlet. So we know the K uppercase E should be equal to the 1, and then it still had loss after the contraction. So HLC should be equal to the KC times V2 square divided by 2G, and from table 10.5 we can determine that the coefficient for the contraction hair loss should be equal to the 0.06. And now we can determine that the ZA should be equal to the ZB plus F1 by D1 V1 square divided by 2G plus F2 times L2 divided by D2 times V2 square divided by 2G plus the K lowercase e times V1 square divided by 2G plus the K uppercase e times V2 square divided by 2G plus the KC times V2 square divided by 2G. And we know F1 is 0.023, F2 is 0.024, V1 is 0.955 meters per second, V2 is 1.698 meters per second, and K lowercase e is 0.5, K uppercase e is 1, KC is 0.06, and L1 is 100 meters, D1 is 0.2 meters, L2 is 150 meters, D2 is 0.15 meters. So we can determine that ZA should be equal to 114.24 meters. And now we need to sketch the HGL and the EGL, and I will plot AGL first. So this is the AGL, and I will use the green to plot the HGL. So dashed green line is the HGL. So we finish this problem.